In this lesson, we'll look at some applications of derivatives. They are related rates. Sometimes two or more variables, they are related. Furthermore, their rate of change, which means derivatives, with respect to time, are also related. And the idea is to find the rate of change of one variable in terms of the rate of change of another quantity. The reason is the rate of change of another quantity, sometimes it's easier to measure, and then the rate of change of interest may be harder to measure. So we find this by using the one that's easier to measure. The procedure is to find an equation that relates two quantities, then use chain rule to differentiate both sides with respect to time. And we'll see a few examples. And oftentimes, when we have related rates problems, here are the suggested steps. Read the problem carefully, repeatedly, until you completely understand the problem. And draw a diagram if at all possible, because a picture worth 1,000 words, right? And then in your reading, identify what's given and what is to be found, and then introduce variables when necessary. After that, you're going to try to find an equation that relates those variables, and this is the equation that you want to differentiate. And then you differentiate that equation with respect to time. Chain rule is used. And then after that, you just use the given information and solve for the desired value. Let's take a look at the first example. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. And the radius r of the outer ripple is increasing and at a constant rate of 1 foot per second. And when the radius is 4 feet, at what rate is the total area of the disturbed water changing? So when a pebble is dropped on a calm water, and it will create ripples, right? So concentric circles. And the radius is getting larger and larger. And so here, what do we know? We look at the radius r. It's very intuitive to assign this the distance from the center to the outer circle, call this as r. It's definitely increasing, and we know that it's increasing at a constant rate of 1 foot per second. And of course, when this circle is getting larger and larger, the radius, the area is getting larger and larger. So the question is, at what rate is the area increasing at when the radius is 4 feet? Now this is the whole question. We try to translate the information using mathematical symbol or mathematical language. So we see that radius r is changing, and how fast it is increasing, 1 foot per second, right? So therefore, definitely it's the rate of change of the radius, which is the dr dt. At different time, the radius is different. So dr dt it's changing at it's changing at 1 foot per second, right? It's given right there. Okay, and then this is telling us the rate. Okay, and when the radius is 4 feet, at what rate the area is changing? The area of the disturbed water is changing. So therefore, we want to see how fast the area is changing. So therefore, the rate of change of area. So we are going to denote it as dA dt. A is usually used to denote the area when r is 4 feet, right? So that's what we want to find. That's what's given, and we want to find that when this happens. Now, time for us to find an equation to connect those variables a and r, because this is a circle. It's pretty intuitive that we should use the area formula. So the area formula is a is pi r squared. And keep in mind, these both a and r, they're functions of t. So if I want to be very rigorous, and actually you should keep this in mind, this a is the function of t, and the r is also a function of t, right? Okay, r squared. Now, next, we want to differentiate this equation with respect to the time t. Okay, so therefore, let's differentiate this with respect to time t. The left side, the derivative of area is derivative of area, right? With respect to time t. And the right hand side, think of this r as a function of t, and the outer function will be u squared, where u is actually this r. So therefore, according to the chain rule, we'll have pi times 2 times r, right? The power rule, general power rule, times the derivative of inner function, which is dr dt. So chain rule is used right there. Now, let's take a look at what we know. We do know dr dt, so therefore we do know this piece of information. And we want to find the dA dt when r is 4. So we just need to substitute the given information into this equation, this new equation, to find the dA dt. So I'm going to say when r is equal to 4, now we can find dA dt, which is pi times 2r. The r is equal to 4, times dr dt, which is 1 feet per second. 1 feet per second. By the way, this 4, the unit is the foot, and here this is the foot per second, right? And then you can see that after you do this algebra, it's going to be 8 pi, and let's look at the units. It's going to be square feet per second. All right, so therefore we can answer the question when radius is 4 feet, the rate of the area that is changing is increasing at 8 pi square feet per second. All right, let's take a look at the second example. A spherical balloon is being filled with air at the rate of 2 cubic centimeter per second. How fast is the radius increasing when the radius is 3 centimeter? So if you blow air into a balloon, it's increasing. So this is a spherical balloon, assuming perfect sphere. And this radius, we want to, let's call it r. So, and we do know the volume is increasing at this rate, right? So therefore, let's introduce the volume, which is usually denoted by V. So dV dt. So that's given. dV dt is 2 cubic centimeters per second. And what do we want to find? We want to find how fast the radius is changing. So therefore, it's the rate of change in the radius. So therefore, we want to find dr dt. So this is what we want. When the radius is equal to 3 centimeter. Okay, with that, next we'll have to figure out a equation that connects these variables, right? And then the volume equation of a sphere is 4/3 pi r cubed. Famous equation, so sometimes you do have to know some basic equations. At the next step, we are going to differentiate both sides. So dv dt with respect to time equals 4/3 pi times, all right, chain rule is used right there. We have 3r squared and dr dt. And then when r is 3 centimeter, and we want to figure out this guy, right? So let's plug in the information for the other known quantity. So we know dv dt, so we can plug in 2 here. We know r, we can plug in 3 here. Now we have 2 equals 4/3. By the way, we should actually simplify this a little bit here. Okay, cancel the 3, so I don't really need to write 4/3. It's just 4 pi r squared, right? So r squared, r is 3, so 3 squared dr dt. We can actually divide both sides by 2. And so we want to solve for dr dt. The equation we have now is 1 equals, this is 9 times 2, which is 18 pi dr dt. And dr dt eventually is equal to 1/18 pi. And the unit will be centimeter per second. Now, let's look at another one. The more different types of problem that you do, the better you will be. So there's no trick. Just do as many different types of examples as you can. This time, let's take a look at with this problem. An observer stands 200 meters from the launch side of a hot air balloon. So I'm going to say, so here this is where the hot air balloon is launching. And this person is standing right there. And from here to here, this is 200 meters. The balloon rises vertically at the constant rate of 4 meters per second. So this balloon is rising vertically at this rate, 4 meters per second. So I'm going to call this height as y. And how fast is the angle of elevation of the balloon increasing? 30 seconds after the launch. So basically, when this balloon is rising, this is the, so when this person is looking at this balloon, this is the angle of elevation. So this angle is getting larger and larger, right? So we want to find how fast this angle is changing 30 seconds after the launch. So therefore, what's given? I'm going to introduce some variables here. We already introduced theta, we introduced the y. So I think this is also changing as well. But for now, we don't really know whether we need that or not. I actually, we'll just see, okay? So for now, it seems like these two are enough, sufficient. So given that dy dt is equal to 4 meters per second. And what do we want? We want to find how fast this angle is changing. So d theta dt when time is equal to 30, right? The time is equal to 30 seconds, okay? Well, time for us to find a function that relates this theta and y. We already know this side. Actually, after 30 seconds, we also know this distance, right? So I'm going to write this at time 30 seconds. The y is actually, you know, v times t. The v times t, the v is 4 times 30 seconds, which is 120 meters. So therefore, this is actually 120 meters. And now, again, a function that links these two together. There are multiple functions, but I probably choose tangent theta because the 200 this side is fixed. So tangent is probably a good function to use. So tangent theta is equal to opposite, which is y, divided by adjacent, which is 200. And then next, we are going to differentiate both sides with respect to the time t. Derivative of tangent theta is going to be secant theta squared. Chain rule is used, times d theta dt equals 1 over 200 dy dt. Now to d theta dt, when we solve for d theta dt, so we divide both sides by secant theta squared, right? So we have 1 over 200 secant theta squared times dy dt. By the way, 1 over secant theta squared actually is cosine theta squared. So therefore, this actually is equal to cosine theta squared over 200 dy dt. All right, we already know dy dt, so we just need to figure out cosine theta, right? So cosine is adjacent over hypotenuse. And this hypotenuse, we already know these two legs, the length of these two legs. So by Pythagorean theorem, this hypotenuse is actually square root of 120 square plus 200 square, right? So therefore, we actually can, so therefore here I'm going to write cosine theta is actually 200 over square root of 120 square plus 200 square, okay? And then because I will square it, which the square root will be gone after square, so I'm going to just keep this for now. So finally, I have the cosine theta square. So here's the cosine theta square. 200 over square root of 120 square plus 200 square. So, and then square, this is the cosine theta, and then I'm going to square it. And over 200, right? So basically times 1 over 200. And then times the dy d theta, and then we do know that this is equal to 4. So times 4. And using calculator, this is about approximately 0.0, like 147-ish. So 147-ish, so 1.015 around. And the rate units is going to be radian per second. All right, so this is problem number 3. Now next, here we have a ladder 10 feet long is leaning against the vertical wall when O1 begins pulling the foot of the ladder away from the wall at this rate, 1 feet per second. So I'm going to again draw a graph. So here there's a ladder and this is the wall. Okay, and then so O1 is actually pulling this foot from away from the wall at this rate. How fast is the top of the ladder sliding down the wall when the foot of the ladder is 6 feet from the wall? So when this is 6 feet from the wall, how fast this tip is sliding down the wall? That's what we want to find. So again, I'm going to introduce some variables. So I'm going to call this as because this is the height, I'm just call it h. If you want to call it y, really up to you. And this is the horizontal one. I'm going to call this as x. Okay, x. So with that, what do we know? We do know that the ladder, the foot of the ladder is leaving the wall away from the wall at this rate. Therefore, it's dx dt is equal to 1. Is equal to 1. This is the given. And what do we want to find? So here's what we want. We want to find dH dt, right? When x is 6. And we also know that this ladder is 10 foot long, so therefore this side is 10 feet. Now we have to find an equation that connects those h and x. So it seems like a Pythagorean theorem is pretty straightforward here. So I'm going to say x squared plus h squared is equal to 10 squared. And now time to differentiate all these both sides with respect to time. So the first one is 2x times dx dt plus 2h dh dt equals, and here this is just a constant, so the derivative with respect to the time is going to be 0. There's no change in the length of the ladder. And you can see that we can divide both sides by 2, cancel out the 2. Now let's solve for dh dt. So we have h dh dt equals negative x dx dt, and then divide by h, dh dt equals negative x over h dx dt. Now when this x is 6, and here we are missing the quantity for h, right? But we can definitely find h using the Pythagorean theorem. So I'm going to quickly find it. So when x is 6, the h, we do know like x squared plus h squared is equal to 10 squared. That means 6 squared plus h squared equals 10 squared. And this is 36 plus h squared equals 100, meaning h is 64. H squared is 64. H has to be 8. So with that, we now can plug into this result. So therefore, this is equal to negative x is 6, h is 8, times dx dt, which is just 1. So 1. And therefore, this is actually equal to, this is cancelled, the 2 is 3/4, which means negative 0.75. And the unit will be feet per second. So therefore, this is how fast the tip of the ladder sliding down the wall. And you may wonder, why there's a negative? What does that mean? So the negative actually means this distance is actually shrinking. Okay, that's what the negative sign means. We finished this particular question. Actually, I would like to encourage you to try to answer another follow-up question. Say, for instance, and here's the follow-up question. What if, okay, what if the x is equal to 9 point, I'm gonna 1, 2, 3, 4, 5, 6, 7, 8 nines after the decimal. What if this distance from the foot of the ladder to the wall is 9 point, there are 8 nines after the decimal feet away from the wall. What is the dh dt? So give a try, and you may find out something quite interesting. And pause the video and then find this and see what you find out. Okay, and in fact you'll find out that this dh dt is huge, which means it's sliding down very fast, even faster than the speed of light. Would that be possible in your personal experience? But if not, probably it doesn't make sense, right? It cannot be sliding down the wall that with a speed faster than the speed of light. But if that doesn't make sense, and uh, what what's wrong with our calculus, right? With the calculation seems to be right, and that's actually a correct calculation there. So leave your comments in the below the video, and then let me know what you think. This is a quite interesting question to ask, actually. All right, let's move on. Okay, let's move on to the next problem. Here, car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Both are headed for the intersection of two roads, and then we want to find what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection. So let's visualize what's going on, and we have two roads, and car A is heading towards the west for the intersection, and car B heading north towards the intersection. And let's introduce the variables. We Here, this is the distance. Let's call that as x, and this is the distance, vertical distance. Let's call that as y. And next, let's try to interpret those given information using mathematical symbol, right? So this traveling 50 miles per hour, this is the rate of change of car A's position. So I'm going to say dx dt. This is definitely dx dt. So this is what's given here. Given dx dt is equal to, you may feel like, okay, I'm going to write 50 miles per hour. And actually, this should be, if we want to be very rigorous, we should be negative 50 miles per hour, because this distance is decreasing, is shrinking. This negative sign means it's shrinking the distance from car A's position to the intersection. So we should use a negative sign there. And similarly, dB dt, well, I'm sorry, not dB, I used the y, so I'm going to say dy dt. dy dt is equal to 60 miles per hour, and you should again add a negative sign because this distance is also shrinking as well. And what do we want to find? We want to find how fast these two cars approaching each other, right? So in other words, the distance is actually this diagonal distance. So I'm going to call this as my z. So this is what I want. We want dz dt equals what? When x is 0.3, y is 0.4. So that's the given information. Now, next, we want to find a equation that relates these variables, right? And it's very intuitive. The Pythagorean theorem can be used. We have x squared plus y squared equals z squared. That's the equation. And after that, let's differentiate both sides with respect to t using the chain rule. 2x times dx dt. So give a try. You can pause the video any moment and give a try first. 2y times dy dt equals 2z times dz dt. And that's what we want to find. Okay. And a quick observation is we can absolutely cancel the two immediately, so that we don't need to worry about these constants. And when x is 0.3, y is 0.4, let's look at what we know and what we don't know. We know the x, we know the dx dt, which is this guy, and we know the y, and given 0.4, and we know the dy dt, which is this guy. We don't know the z yet, right? So at that moment, but we can definitely find the z using this equation. So when x is 0.3, y is 0.4, then we have the following. 0.3 square plus 0.4 square equals the z square, and find the z. And because actually the this ratio, like when this is 3, this is when this is 0.3, this is 0.4, this has to be 0.5, and there's a famous right triangle, the size is 3, 4, 5, but you can use this to verify. It turns out z is 0.5. Now we're ready to plug in all the values. So when x is 0.3 times the dx dt, which is negative 50, plus y is 0.4, dy dt, which is negative 60, equals z is 0.5, and dz dt. And so we can actually, so this is negative 15 plus this is negative 24, so basically minus 24 equals 0.5 is 1/2, right? Times dz dt. And the left side gives us 39, okay? 39, negative 39 equals 1/2 dz dt. And therefore dz dt is equal to negative 78 and miles per hour. That means these two cars, when the negative sign means the distance between the distance between these two cars is shrinking, is decreasing at the rate of 78 miles per hour. All right. Lastly, we are going to look at another pretty popular problem that involves a cone. Okay, that involves a cone. Water is draining from the bottom of a cone-shaped funnel at the rate of 0.03 cubic feet per second. The height of funnel is 2 feet, and the radius at the top of the funnel is 1 foot. So in other words, let me label that. This is 1, and this height is 2. And of course, the water is draining from this cone, and therefore the water level will be decreasing, right? So here's the question. At what rate is the height of the water in the funnel changing when the height of water is 0.5 feet? In other words, when the water level is here, and when this is 0.5, how fast this water level at that moment is changing. Okay. All right. So a little. Let's first identify what's given. And we do know that the water is leaving the funnel at this rate, and this is volume, the cubic feet per second. This is how fast the volume is decreasing, right? So therefore, I'm going to say dV dt is equal to, hopefully at this moment, when you see something that's you're losing the water and the volume is decreasing, you are adding a negative sign to represent that idea. So negative 0.03 cubic feet per second. And what else? We want to find that, of course, we know the shape of this cone, and we want to find that how fast the height is changing when the water level is 0.5 feet. So in other words, we want to find, let's label this as the height at any moment as h. So I'm going to draw this is my radius, this is 1, this is 2. So at any moment, and this height, let's call it h. Okay, let's call this height as h. And at that moment, let's call the radius at that moment as r. So we want to say dh dt, what is that quantity when h is 0.5? The unit is foot. First of all, the volume of remain in the funnel at any moment. The volume formula is 1/3 pi r square h. That's the volume for a cone shape solid. And now you do see that we have three variables, right? And we are in a single variable calculus, so we are not able to handle multiple variables like that. So therefore, we have to reduce the number of variables in this equation. And we do have a relationship here. And the relationship is the radius and the height, the ratio of the radius and height in this cone. So in this case, at any time when this is h, this is r, this triangle should be similar to this bigger triangle. So with that, we can see that radius should be half of the height. So using this similar triangle, so we use similar triangle. We do know that the r over h should be equal to 1/2, which means r is equal to h over 2, or you can say h equals to r. I do want to eliminate r because I want to find dh dt, so I don't want the r. That's why I use solve for r. Now after that, I'm gonna do this substitution. I'm gonna plug this in here, right? So that my volume becomes 1/3 pi times r square times h, and what is my r? H over 2. And let's simplify this a little bit here. So therefore I have okay, let's do a little. This is 2 square is 4, and then times 3, this is 12. So I'm gonna have 12, 1/12. Pi times, and I have h squared times h cubed. So this is the single, this is the volume that involves only one independent variable h here, no longer two variables. Next, we need to differentiate both sides with respect to t. So dv dt equals 1/12 pi times 3h squared, right? So 1/12 pi times 3h squared times dh dt, and which is actually 1/4 pi h squared dh dt. Now, I think we are ready to find the dh dt using all the information given, right? So we have dv dt is negative 0.03 equals 1/4 pi times h is 0.5, and then square it, dh dt. And therefore, we are gonna solve for dh dt. And this is negative 0.03 equals 1/4 pi times, this is 1/2. 1/2 square is actually 1/4, right? So basically this is 1/4, and 1/4 dh dt. And this is 16 over here, 1/16, and pi. Let's solve for dh dt now. Dh dt, and on the left side, on this width here, this is 1/16 pi equals negative 0.03. So therefore dh dt equals negative 0.03 times 16 over pi. If you use a calculator, this is about negative 0.153-ish feet per second. And again, the negative sign means the water level, the height of the water level is decreasing.